Hello and welcome back. In this episode we are finalizing our one-way rigid fluid coupling so that we have a basic collision for our particles against our shapes. So let's jump right to the code and implement that. Okay, back to Visual Studio. In the simulation class, I first want to comment spring things out and the viscosity, because I just want to have a normal fluid in my browser. Yeah, that looks a little bit better. And then we need to do some things in the circle.js and in the shape class. In the circle, we have to create a new method, and this will be called getDirectionOut. And this method will get, well, it's already saying everything. This method will create a vector, and this vector has every information we need to push a particle out of a shape. Okay, and this vector is based on the on the shortest way out of a shape. In the circle, that's luckily easy, pretty easy. In the circle, we just need to define a direction from the particle to the center of the circle, and then we can check if there's a collision, just like the isPointInside method we did in the last episode. And if it's smaller, if the particle is in the circle, then we can get a normalized direction by normalizing the direction, and then we just have to flip this direction. Well, depends on how you calculate the direction vector. And yeah, then we have everything. We just need to multiply this normalized direction with the penetration depth, which is just a subtraction from the radius and the length of the particle and the circle center. And then we have the direction out. Yeah, so let's implement that. All right, so get direction out. This is going to have a position. I'll let this call pos, like the isPointInside method. And then I have a direction, and this direction, I'm gonna say this direction is the position subtracted by this dot position. Okay, so the particle position minus this dot position. Then I'm going to check if there's a collision, and I can do that by saying direction.length2. I'm doing the optimized way, is smaller than this dot radius times this dot radius. You can also do just use the length and with one radius without the multiplication. That's also fine, but the other way is a little bit more optimized, because here we are not using the square root, and this is usually a bit more involved for the CPU, so it's going to be a little bit more performance. We get a little bit more performance out of that. Then we can calculate the penetration. If there's a collision, the penetration will be this dot radius minus direction dot length. Length. All right. What does this mean? The direction dot length. We know that if there is a collision, then the particle, well, the direction of the center to the particle, the magnitude of this direction is or must be smaller than the radius. Okay, then there is a collision, as this line states. And this penetration is simply a subtraction from the radius with this magnitude. This is the rest. If you, well, yeah, that's everything. Maybe if you still have troubles to understand this, try to take a paper and draw it. Then it's gonna be clear. I did that too when I started with physical things for circles, and that helped me a lot actually, drawing everything on a piece of paper. But yeah, just radius minus the directional length, that's the rest, and then you have the penetration. And then we can normalize the vector, the direction. And then we can say direction, we want to scale the direction by the penetration. Okay, so that our get out direction or our out pushing vector will have the magnitude of the penetration, so the particle is just pushed enough out of the circle, just at the corner of the circle. And yeah, then we can return the direction, and that's everything. We also need to return null if there's no collision. All right, and this is our get direction out. And I wrote this one wrong. There we go. This is our direction out for the circle. For shapes, it's a little bit more involved, unfortunately. Let us first define the method for shape. And in here, we also create a new method, and I'm just going to copy this one. And I'm going to return null for now, because I want to test and I want to implement everything in the simulation class first and test it with the circle, because that's the easiest. And then if that's working, we can try figuring out how we can do that for our, well, polygon shapes. All right, in the simulation class, I think we don't have a handle one-way method. Nope. All right, then let's create a new method, and this will be called handle one-way coupling. And this one-way coupling is a expression or a word you will read a lot if you're doing things with fluid simulations. If it's just if it's a smoke simulation, a grid-based simulation, basically, or something hybrid or a particle-based simulation, there always will be this word one-way coupling if it comes to collision detection between particles or the simulation and rigid bodies or other geometry things, except for the border, probably, because the border can't move. And, well, kind of. And one-way coupling means just the particle can be moved by an object, but not the other way around. Okay, that's why it's called one-way. The particle can be moved by the object, but the object can't be moved by the particle. And if a object can be moved by a particle, then it's called two-way coupling. All right, so there are two ways objects can move, or, well, yeah, they can move each other. And that's why it's called two-way coupling. And for our simulation, it's called one-way coupling, because just the particles can move. Yeah, and the objects can't. If we want to implement the two-way coupling, we have to do a lot more things. We probably, in this case, in this scenario, we should add our physics engine in the other tutorial to this one, but this is more complicated, and to be honest, I didn't really figure it out how to combine these two things properly. It kind of works, but not that really good. This is something for the future, probably. Okay, so enough talk. Let's implement the handle one-way coupling. Here, first we need to iterate again through all the particles, and also for some performance thoughts, you should use a spatial grid for your objects, store the objects into the spatial grid, and use this one to get the neighboring particles of an object. You shouldn't use it like I'm doing, because this is just, well, for educational reasons, I'm going the simpler way and just iterating through every shape with every or against every particle. And it's going to be way better if you use a optimization structure like spatial grids or hash grids or something like this. Just like I did in the other tutorial. That's probably the best thing you can do. It's really similar. All right, then we will retrieve the particle, and this is this dot particles at the index position. Oops. There we go. And then we have another for loop, and here we are iterating through every shape. And now I can get the direction out. Direction out at the particle position. Okay, I'm just making sure that I wrote that right. All right, good. And then if the direction is not null, that means we have a collision, and then we can say the particle position. I'm going to add the direction, the movement to the particle position, and then I'm going to set that. Okay, and that's everything. Yeah, let's see if that's working. Okay, apparently it doesn't. Yeah, of course I know why. We of course need to call this method, and yeah, that we can do that by saying the one-way coupling should be done before the word boundary. You can do that the other way around too. All right. And then if we go to the browser, don't forget to save and refresh. Let's go to the browser. There we go. This is our simulation. We don't implement that we didn't implement our things for the shape class, so the rectangle doesn't do anything. And yeah, this is our typical fluid. And if I take the circle now, then we can see we have a collision against our circle. Cool. All right. Yeah, that looks really cool. All right, then let's go and implement the same thing for our rectangle, or for any polygon you like, except concave polygons. So back to Visual Studio. Let's go to the shape class, and here we are currently returning null. And this is now a little bit more involved because we first, well, actually, it's kind of similar to is point inside, because we need to do the same operations. But what we need to do is we have to find the best edge of the shape. Or let's say the smallest penetration depth. So basically the best position or the best vector to push out the particle. Because technically, if a particle is inside a rectangle, you could push it out on every side. All right, you can push it out. Let's say you have the rectangle in our simulation. It's a axis-aligned rectangle, and if a particle is inside, you can push it out on the right, on the left, on the top, and on the bottom side, technically. Okay, but we want to push it out at the side where the penetration is the smallest. And we have to find the right edge for this. And for this, we can actually copy a lot of things from this point inside method because we are doing the most important things already. That's quite cool. So let's copy first the for loop with the vertex and the normal and just paste it in. And then we can also copy the vertex to point and the dot operation. And now I can already say if the dot product is greater than 0, then we can return null. This is, I think it's the same thing. Yeah, it's the same thing like in this point inside method. Here, instead, we are returning false, so no collision. It's kind of the same. We're returning null, or there is no vector to push out, okay? And in the else case, we have a case where the point is inside an edge, but we have to check if the dot product is actually the smallest value. And we can do that with an else if. But before that, we have to declare 2 more variables, and one of them is the best normal variable. This will be used to store or to calculate the best normal. Well, actually, it's not going to be, we are not calculating the best normal, we're just copying the best normal, okay? That's the best normal is the normal on the edge. And the edge, well, the normal which is the appropriate normal to push out the particle. That's why it's called best normal. That's the best position or the best direction to use to push it out. So if a particle lies on the top edge or in the near of the top edge, then the best normal would be the normal of that top edge. All right, then we have a really small number. And this is in JavaScript, this is number.maxValue and negative. I'm not quite sure what's the similar thing in Java or in C# or even in C++. I'm not quite sure. You can also use just a really large number like minus 100,000 or something. This should work too easily. But I'm going to make sure I'm using the maximum negative value. But yeah, you can use any really large negative number. It's okay. And with this in mind, now this one has a really negative number. And now we can see if we get a little bit a larger number, but still in the negative, okay? We have to search for a value which is larger than this number currently, but is still penetrating the object. So this number must be negative, but the largest negative value. And we can do that by saying in the else if the dot product is actually larger than the smallest value. Okay, the dot product, if this is the case, or if the dot product is greater than 0, then return null. So in this line, the dot product must be negative or equal to 0. That's also fine. And well, actually, I think this value should be greater equal to 0. Because if the dot product is 0 in here, because we need to scale the normal, and if we scale the normal by 0, that's not going to be a good vector. It's going to be a 0 vector. Well, actually, I think it's yeah, we can leave it like this. This should work too. Well, anyways, this line says that the dot product is smaller than smaller than 0. But if the dot product is also greater than the smallest number, and the smallest number is currently a really small number, so this is going to happen for sure if there's a collision. So we say the new smallest number is the value of the dot product, okay? And we're also saying the current best normal is the normal on that edge. And I'm just going to copy the normal in this new variable. And if we find in another iteration, if we find another value, which is even a little bit greater than our dot product. No, sorry. I mean, if the dot product in the next iteration is a little bit greater, but still in the negative, then then this statement is again true, and we save the next best smallest number. All right, and then when we iterating through this, then we will find the best normal to push out the particle. All right, and that's it. Then we have to just say if the best normal is actually null, then we have to return null. So I'm saying, well, if the best normal is null, then return null. All right, and else we can say that the normal will be scaled. Ah, damn it. Scale, come on, there we go. We can say that the best normal will be scaled by the smallest number. And now we might need to multiply this by -1. This depends on how you create the direction vector. In my case, I have to multiply it by -1 to get a right direction out vector. If you don't multiply it, you might have a vector which points inside of that shape, but we want a vector which points outside of the shape. That's why I'm multiplying this by -1. All right, and that's everything. I hope this works. Yeah, let's go to the web browser, refresh. And, oh, I already got an error. All right. Position is not defined. There we go. Yeah. I have to set the position from the parameter. All right. So let's go to the browser again. And there we go. I already refreshed it. And you can already see, we see our collision now happening with our rectangle. And just to show you that it's working not just for rectangles. I mean, of course, it's a polygon, but I'm just going to delete one edge of the rectangle. So there we go. We have a rectangle. Sorry, a triangle now, and yeah, it's working pretty good. Cool. All right, and just one small addition. I want to draw the particles in front of the shapes. So you don't see that small clipping here, okay, where the particle is inside of the shape. So I just want to draw the particles in front of the geometry. And we can do that really, really simply. I'm just saying that the shapes, all of the shapes will be drawn before the particles. And that's everything. If you go back to the browser, refresh, and there we go. Our particles are now drawn yeah, before the other things. And this is our one-way rigid fluid coupling. We can play a little bit around. For example, I can increase the emitter. Where was it? There we go. The spawn interval, let's say to 0.5. I want the amount at 10. And yeah, that's it for this episode. Already, the last one was a bit longer. This one is, I think, already 25 minutes. Yeah, thank you very much for watching, and I hope to see you in the next episode. Have a nice day, and bye-bye.